Um, so my name's Nikki Eno. I'm the current chair for SEI for the 2023-2024 year. We have most of our board on the call. Keith Merrill is our vice chair. Mike Urban is our treasurer. Colin Drager serving as our secretary. Greg Dunn is our program director. Director of Public Relations is William Kittleman, and we have Alex Domino joining us this year on our board as Deputy Director of Public Relations. So I want to take a minute to acknowledge our annual golf outing sponsors. Every year we've been holding a golf outing to raise funds to support our student scholarship that we give out every year. This year our golf outing is going to be held on May 10th. So hopefully everyone can attend. Save the date for that. And last year I want to acknowledge our scholarship sponsor, which was our highest sponsor, which was AECOM. And then we have our additional table sponsors, whole sponsors, and prize sponsors from last year. So big thank you to all of those companies for supporting our scholarship. So again, welcome to our presentation, our lunchtime design seminar for today. Just a reminder, if everybody can please mute yourself when you're not speaking. Any questions that you have during the presentation, you can place in the chat. And we can address it at the end. And if you have any follow-up comments, they can also be sent to our Gmail address or directly to our presenter, John Roach. So today's topic for the presentation is the CHOP Schuylkill Ave Research Building, which is a design of a high-rise lab building above an existing podium structure. Everyone on the call today will earn a PDH, and you can download the PDH certificate at the website shown here, which is on our SEI website, or we'll also be pasting the link in the chat window at the end of the presentation. And our speaker for today is John Roach. He's a structural engineering project manager at Canon Design. He received a bachelor's and master's from SUNY Buffalo and is a licensed PE in several jurisdictions. Over his career, John has worked on a wide range of projects with a focus on large, complex healthcare and scientific research facilities. And he has been the structural engineer of record and lead engineer for the CHOP SARB project since design began at the beginning of 2021. So at this point, John, I'll stop sharing my screen and turn it over to you to give your presentation.
All right, thanks, Nicole. I'll attempt to share, and hopefully that goes okay. Okay, so everybody should be able to see my screen now. So yeah, thanks, Nicole, for the introduction. Can you see my screen?
Yeah.
Okay, great. Thanks, Nicole, for the introduction. As I think a lot of people are familiar with Children's Hospital of Philadelphia, we all know as CHOP, and we're going to be talking about the Schuylkill Avenue Research Building. So another acronym, we're just going to call it SARB. Again, just a little about myself. I've been with Canon Design for almost 13 years now, and I've been working on this building for close to 3 of them. I've contributed some articles now and then to Modern Steel Structure, did a podcast once. And just a little bit who we are. We're an integrated AE firm with a little construction consultancy, different business modules there below. So we've been around for a little over 100 years now, and we're excited to be doing this project with CHOP. So I'm hoping everybody takes away something good from this, but a couple of highlights. We're at a time right now where we're talking about repositioning real estate across the country. And there are a lot of strategies that go along with that, a lot of pitfalls that owners don't always realize or architects don't always realize. And along with everything here, I hope you keep that in the back of your mind with this, because we're going to be talking about how we're building a research tower over an existing podium structure that, well, we'll get right into it. So the Children's Hospital of Philadelphia, CHOP, if you don't know the history, this is the first American children's hospital, founded in 1855. They've been doing dedicated research here since 1922. So last year was a big year for them. It's the centennial, which is part of the celebration of this building. What you see on the right is actually the first research building that they opened in 1954. So a little bit different than what we're used to seeing today, but a lot of hard work from scientists go into these buildings, and the great work that goes on here really has led to some revolutionary treatments from right here in Philadelphia. So with that in mind, this project is all about supporting excellence in research, bringing researchers together, creating a world-class research destination, because CHOP is a world-class research institution and pediatric healthcare institution. And we want those researchers to feel supported by CHOP as an entity, and also by the building that they're working in. So how can we use the built environment to foster personal development, professional development, connection, and energy and excitement that can help lead to breakthrough discoveries? So a tall order for a building. And the building is located, for those of you familiar with the area, this is South Street Bridge, Schuylkill River. The CHOP main campus is on the other side of the river. This is the Roberts Center for Pediatric Research. And this was built in 2017. I don't know if we have anybody from Thornton Tomasetti on, but they were the structural engineer for this building, along with Ballinger as the architect. And this Podium building in blue was built at the same time. So the site looks like it's sloping, but it's not really. Grade is out here at Schuylkill Avenue. And then because of the bridge abutment where it approaches and comes down the river, it actually slopes 2.5 stories. So when you look at the site, there is, we call level B in red is at grade, true grade. And then level 1 is matching roughly the bridge elevation, South Street Bridge. And then you have all these other intermittent levels. Level A is between level B and level 1. And then you have these areas that pop up above level 1 for the garage entry. Is this podium, the single-story podium structure has levels of a garage within it. And this sort of wraparound soil berm along Schuylkill Avenue. So that's a lot of information. This is what that structure looks like. And maybe for some people, this is a little bit clearer. We're looking now just at that same view. You can see here's that ramp that goes down to the garage. And then there's the level 1, which is the current roof, future level 1. I've highlighted the blue columns to show what are gravity columns for the building. And then in sort of that salmon color is where a future braced frame core would be when this gets built as a tower. What's important to understand is the original intent was that this would be an office tower, just like the Roberts building next door, or possibly a hotel tower. And so the footprint of the building, the core location, everything was sort of predicated on that eventual use. And I say future brace frame core because everything was just designed as a moment connection for the interim condition, just being a podium for a few years till the next building got built. The expectation that the braces would get installed at a later date when the tower was designed. So the project, as we approached it, was essentially 8 stories of standard lab space, 2 stories of specialized research, so a total of 10 research floors with mechanical floors at the top of the building and in the middle, and then carved through that podium, within that podium, all around that podium, preserving as much of the parking as possible, but putting a lobby in there, getting in a platform technology space, which is here labeled as imaging core, essentially various specialized research functions that have like a makerspace lab and 3D print that all the researchers can use. Welcoming entry plaza for people, and then the second story to have a lecture hall and conference space to support this building and the building next door, and really the whole broader CHOP enterprise. So going back to what I had initially said, this was designed to be an office building or a hotel. And if anybody's done a research tower or any kind of research building, the needs are a lot different. You know, this had a lot of long 45-foot bays, which are great if you're putting offices around the perimeter of a core with elevators and things, but terrible if you're doing research labs. Trying to get the vibration of something like that to work out is always a challenge. And the fact is, for a lot of wet bench research laboratories, the space in the middle of the building is just as or sometimes more valuable than the space at the perimeter, because you need functions that are away from light, climate controlled, very away from where a lot of people are walking, where there's a lot of traffic. So that in and of itself created some problems. And then just the unusual shape of the building, right? This is sort of a teardrop shape where this is the test fit of research labs in that building superimposed on the structure. And you can see in red where those braces would be, all around where the elevators would be. Again, makes a lot of sense for an office building or a hotel, but you can see how in blue where the research area is how separate that is from the workspace, the dry lab, the computational lab. And just that disconnect just goes against a lot of what we're trying to create here by building that sense of connection. So how did we get around that? Well, the first thing was talking to Chop and talking about how, okay, what if we think about this building differently? Instead of just a vertical extrusion of that podium with that floor plate you just saw, what if we superimpose another floor plate on top of that? What would that look like? And we actually used parametric design to do that. We looked at what columns need to stay where they're at, where can we change the grid, and what would an expanded building footprint look like without changing the overall floor area? How can we reshape it to get to that? And oh, by the way, do this on an 11-foot planning module. All these requirements are just parameters, right? And that's what parametric design is. So we ran a whole bunch of different optimization scenarios using Rhino and Grasshopper, and we got to this shape, which seemed to satisfy most of those constraints. The columns that couldn't move, minimizing the amount of new foundation requirements, new foundation construction, maximizing the amount of wet lab grids, those 11 by 11 modules that we could fit in a floor plate. And we came up with this. And what you'll notice is that we've got all the computational area, the desk space over here on a long 46-ish foot bay that's over the drive aisle to the parking garage, because can't really drop a new column and shorten up that bay there. It would be in the way of the cars. But then the rest of this, we're able to regularize, at least within the parameters of this footprint. And then even though these sides look arbitrary, it actually is the same curtain wall module on every single side, 3 convex, 3 concave, but the same dimensional module between mullions. So for a unitized curtain wall system, that's important. So a little video kind of showing you around the building. And part of the reason we reshaped it the way we did was not only for the lab, but to give the neighborhood a little bit of breathing room. You can start to see all the low-rise townhouses in the neighborhood. Peeling it back a little bit from that lower corner just gives South Street a little room to breathe, and then creates a really, really cool roof terrace that you'll see some renderings of. So floor framing, we'll get into the gravity system. The pink columns are the ones that we did not change. These stay where they are because there's nothing to transfer them to. They're either part of the brace frame or across the drive aisle. The orange ones represented an opportunity to do some transferring. We could do something with a truss or transfer girder. And then the green ones are the ones that require new foundations. Again, part of the goal of reusing this podium structure was to minimize the amount of new construction. So we really wanted to limit the amount of new foundations we created. Schematically, what this looks like is you've got this area that's more original to an area on the lower right that's less original structure. We manipulated where we could, and we kept where we felt like we had to work within the constraints that we had. So there's this spread across the building where it goes from this purely optimized in the lower right to, we got to work with what we have in the upper left. And it's sort of finding that middle ground, finding that sweet spot for what is the right amount of restructuring of this project. And again, just to superimpose what that looks like, this whole area in blue is ideal for wet bench research, right? We've got these 33-foot by 33-foot bays, more or less, at least they're square or rectangular, and they're at least 11-foot modules in one direction. And then in green, we have the computational research, basically office space where it doesn't matter as much about floor vibration. It's not as sensitive. It's just occupant comfort versus vibration criteria A, VCA, which is 2,000 microinches per second. So being able to use that reconfiguration to our advantage to maximize this available research area. And, here you can see how, even though it goes through the brace frame core in this one area, it connects, right? You have this good connection between the wet bench research and the labs and the computational area. So going back to the brace frames and the lateral force system, one of the challenges that came up right away when we expanded the floor plate to the east and peeled it back from the north was that if you extended these brace frames all the way up, you move the center of rigidity pretty significantly. And in a high rise, 17-story building, that torsional effect at the top starts to become pretty significant. So we looked at, well, what happens if we put a new brace frame out in the new construction? That resolves the torsional issue almost completely. And it also opens up this bay a little bit more so we can get some specialized lab functions in there, cold rooms specifically, minus 80-degree freezers. So that worked out pretty well. Just give us a little more floor space. This is what it looks like. It's a little hard to see on plan, but this is what it looks like as an axon view. So again, in the salmon, that's our original structure. In the blue are the gravity columns that are existing. The dark red is the new structure, including the new braces that are down here in the podium. And you can see this new brace frame out here that we added. And again, this is where it is on plan, just for orientation. So let's zoom in a little bit on that core. What's going on here? Well, if you remember from those previous floor plans, that teardrop shape, each column grid is curved, right? It curves away from one another, and we're trying to superimpose grids on this curve. So when we did that whole optimization, the parametric optimization, the idea was, well, if we can, they're almost in a straight line. What if we can get them in a straight line, get these columns in a straight line to help give us some more regular bays in the lab area? So to do that, we have to look at these brace frames almost as transfer trusses. They are transfer trusses. And this is actually a 14 by 605 that comes down here and then slopes and becomes part of a truss. So this is what it looks like, right? This is our brace frame column, comes down and slopes, continues down, connects and splices with the existing column. And then once it's above level 3 here, we're on that repeating grid. So now we got a real lab building. We got lab space above level 3 on a regular grid, and everything that happens below level 3, if you recall, that conference space, the lobby, everything else, it's not as crucial. We can work around that. And so this is essentially a transfer truss integrated into a brace frame. But, how do you connect a 14 by 605 through all this junk that's happening there? I mean, this is what that connection looks like. And in some cases, you have sloped and skewed braces hitting the same node. So you got a triaxial force condition, more than 3,000 kips. We thought, well, what if we just simplify things and use a solid steel forging, just a big old block of steel? We had a company outside of Pittsburgh do this, Elwood Specialty Steels. It's a 50 KSI steel block, just 4,000, 5,000 pounds of steel, and it just saves so much shop labor. Just some simple plates welded onto this. You can imagine what this would look like with all the stiffeners and continuity plates you would need to do this a conventional way. This is a few more pictures of what it looks like. On the left, you can see that truss before it gets trussed. Another situation we ran into, remember I said that all the original connections were moment frame, right? They didn't have the braces for the future build out in this initial phase. When they did the moment frames, though, they weren't all just simple flange welds. There were a number of bolted beam flanges. So you have this beam column condition, and now you got to turn it into a beam column brace condition. So how do you attach the gusset plate to that when you have that flange plate with, 14 bolts? Well, we did some finite element analysis on this, and so maybe we can just cope that plate and make the plate thick enough to get around, redistribute the force around that flange plate, leave the flange plates in place, and use those to our advantage because, we've got big axial forces that we got to transfer through here, got beams that if at all possible, we don't want to have to go in and reinforce this existing shear condition, start throwing on doubler plates and all that. So we did plastic analysis and finite element analysis, looked at the force distribution, sized the welds. We came up with a minimum gusset plate size, a minimum weld size, did the buckling analysis, and then provided this information to the steel fabricator. So basically, we left the brace to gusset connection to be delegated design. They can do that however they want. And then we sized the gusset and the welds to make the force distributions work, leaving all the existing structure in place. And I think there were only maybe three beams that we had to add stiffeners to. So when you consider the whole quantity of connections down there in the existing podium, it was a big time and money saver for sure. And this is what one of those looks like. So some great field welding, big old gusset plate, and the existing condition here. It's a little smaller flange plate, but you can see what's going on. Okay, so let's go back to that axon view, our overall lateral system, and talk about the front braced frame. So again, this was a great solution to take a little force out of the existing braced frame core, help with those overturning forces, mainly to reduce the torsion and drift. But this will become clearer in some of the other views where we're expanding the footprint of the tower. Again, lower right image. The existing podium is not expanding. So we've got this tall unbraced height where we have just these columns down as a colonnade out in front of the building, supporting a tower like one of those houses on stilts that you see near the ocean. And making that into a braced frame, we have these very acute angles. These braces come down at 13 degrees. So that's not a standard condition. So we came up with these connections where we're basically clamping the brace between a couple of flanges that weld directly to the column, and then take out the uplift through the anchor bolts, and then have a couple of angles welded to an embed plate in the concrete caisson cap and welded directly to the base plate to take out the shear. And that's what this looks like. So they're not tiny. These are almost 7 feet tall. And it is a dramatic design feature that I'll show a little rendering of later on. But to go back to the overall lateral system, extending that axon view up the building, one of the things that became pretty clear was you really want to limit building drift when you have sensitive research occupancies at the very top of the building. Experiments and things like that can be more sensitive to humans than acceleration. So we wanted a very stiff building, and the way to get that here were pairs of outrigger trusses at the mechanical floors. We got a 2-story mechanical high space at level 7, so 24-foot high outrigger roughly, and 20-foot high mechanical space at the top of the building for basically a hat truss. And that really, really reduced drift, stiffened things up, and also really reduced the overturning uplift forces on the existing foundation. So we were able to work within the existing caisson capacities and everything else down there, not overstress the columns. Those outrigger trusses is what they look like. Fairly straightforward, going from the brace frame core between grid XC and XD and the tower portion of the building, the further out floor plan, all the way to grid XA. But there's actually a truss within a truss. So we realized that there was an opportunity here with the outriggers that, well, as long as we're putting them in, why don't we have them carry some load too, and further minimize the amount of new foundations we need to do outside the footprint of that existing podium. And so we integrated a hanger truss into the outrigger truss so that there's a column below, you can see in this image, that is hanging from it, and a column above that transfers out. That's these two columns right here. And so what that does is, aside from avoiding the need for new foundations, it opens up this big room on the second floor where otherwise I would have to either have a transfer truss or a column coming down through, or I can have an operable partition, give CHOP a facility that they don't really have right now, which is this, it's actually 2 pairs of symposium rooms that can open up all the way down and accommodate huge groups of people here for conferences. And this is what it looks like in axon view. So in green, you can see that hanging column or transfer column. It works together with the truss at the top of the building and the truss at 7. And then at the very bottom of the green column, that big old gap area where we have that big symposium space. And this required a lot of a construction staging analysis, looking at the building when we would just have temporary shoring at level 3, then the column going up to where the truss is before the truss is built. Then once the truss is built, then after the truss is built, the next layer of the next stack of column going up to the top of the building, and then everything all at once acting as a finished structure. And of course, it's not just taking gravity load, but also lateral load. So lots of different models to look at what the deflection is, effects of axial shortening, everything like that. And what we ended up doing was, this is just a zoomed in version of that level 2 space. What we ended up doing was settling on an approach working with the steel erector where we actually erected temporary trusses below level 2. Everything below level 2 here goes away in the finished state, but they support a temporary column that the hanging column sits on. And we have hydraulic jacks on these, sized for, I think, 500 kips. And the idea is that, that'll be not only the temporary support, but you can tune that jack, right? Is axial shortening, there's a lot of effects that are not perfectly possible to predict, but the jack will give you a little bit of flexibility, and you can get things level by the time you get up to level 7 to erect that first transfer truss. And this is what it looks like. So all these trusses hanging below level 2, temporary, just to support those jacks. But it opens up a whole area on a very congested site for construction equipment and drive aisles below the building here. So that was a secondary benefit, not having to do any kind of shoring. So I mentioned earlier that there's sort of an aesthetic appeal to this, and I think this explains it better than I could with words. You've got the existing podium reclad in glass down here, swooping below the tower, and this 50-foot-ish colonnade out in front that creates these sheltered areas for outdoor learning spaces, amenities for the neighborhood, circulation around the building, and the brace frames just architecturally expressed. All right, one more column transfer to talk about here, a little bit more straightforward than the other two, and then one in the corner as well. Just a simple transfer truss at level 2. So you have 2 symposium spaces where I'm standing with the camera, and then 2 symposium spaces beyond this truss. The truss sort of divides the 2 of them, but they could be combined. There's enough room to walk below this too. So future flexibility is accommodated if they ever wanted to make it 4 big spaces. And then just I think a clever condition here out at the corner of the building. We use this column here as one of the anchor points in that parametric optimization model, and said, okay, this column wants to be right here. Why does it want to be right here? Because we have 2 columns that exist right between it. And so we can anchor the corner of the building with a new column, use these existing columns and foundations, and turn the whole thing into a transfer truss. So you got this existing beam down here. The only thing it's doing is supporting this gusset plate, and then new truss members on top of it. And it's that simple. All right, so foundation strategies, talk a little bit about those. We were able to reuse all of the existing caisson foundations without overstressing any of them. But again, we did need to add a handful of new foundations, I think 7 in total. And we did micropiles for the gravity columns and caissons for the lateral system to take out the base shear. But for those micropiles, got the drill rig in the building, drilled right through the slab on grade. And in many cases where it was just parking area, we were able to locate these pile caps to be in between parking spaces. So we actually didn't have to excavate for them. We were able to just cast them right on top of the existing slab and keep them high. So that eliminated some of the site work that would have otherwise been needed. So there's that drill rig. You see it start shooting mud everywhere. It goes up, hits the ceiling. I think at this point, the underside of that existing level 1 deck is entirely coated in mud. But yeah, it's a noisy process. I don't know if you've ever seen one of these, but they're pretty cool to watch. What those pile caps are, so you can see on the left a couple of pile caps that are below grade, and then on the right, one that's above grade that wasn't in the way of anything. So we're able to just do a little less excavation. And now out at the front, that's a different story. Again, we have fairly high base shear from those brace frame columns. So we did, well, the intent was to do 3 new caissons there. We didn't get that lucky though, because right below, directly below one of those columns is a medium voltage service duct. So those are difficult to move, and you generally don't if you can avoid it. So we ended up doing is a pair of caissons to span over these 2 duct banks, and one 6-foot diameter caisson, another 6-foot caisson with this big grade beam between the 2 of them. Again, it's like 3,000 kips coming down on this thing. So the grade beam was designed. We did strut and tie analysis. It's about 10 feet, 10 and a half feet deep, section through it, and a whole lot of bar at the bottom. But they built it without any issue. This is that area under construction. On the left is one of the 8-foot diameter caissons directly below a column, and then the 2 6-foot diameter ones with the duct bank roughly in between them. This is that grade beam in the field. So again, this is 10 and a half feet deep, big chunk of concrete, and then the duct banks below it with some rigid insulation to provide some separation, and then a manhole right here that remained in place. Now, the rest of the foundations, going back to that area of the building that we didn't touch, we looked at those columns, and in some cases we had to reinforce some columns, throw some plates on them. But in some cases, we had to also reinforce the foundation column interface, because not that the base plate didn't have adequate capacity, but that because it was a square base plate on a circular concrete pier, there wasn't enough bearing area, and it was actually overstressing the concrete. So we looked at a few things, and it ended up, the simplest solution was just to provide more bearing area in the form of expanding the plates. And it's a detail we've had to do before on these kind of vertical expansion projects, where we added some expanded bearing area and then stiffener plates for load transfer to take the load out of the column and transfer it to the new plate. We validated it with some finite element, but just some good old hand calcs to make sure it all worked, using elastic methods and beam, essentially treating the plates as beams and checking shear and everything, and some spreadsheets. It's a belt and suspenders approach, but this is what it looks like in the field, right? You got these stiffener plates welded onto these base plates for transfer, and here you can see this is an example of a column that we had to reinforce with a cover plate for weak axis buckling. So talked a lot about all these different structural retrofits and all the hoops we had to jump through to put this tower on this podium. And, maybe it seems like it's a lot of effort and it's a lot of work, and why would you do this? I think it's not to sound like a cliche or trite about it, but it's about making lemonade out of lemons here. And as we worked through conceptual design and schematic design, we realized this presents a whole lot of exciting design opportunity, right? And I think this is something that all of us need to think about when we're working with existing infrastructure, that the constraints sometimes offer a really great opportunity for design creativity. So one example, we have this two-story space, level 1 to level 2 of the building, 24-foot high floor to floor, mainly so that it matched the building next door, so that in theory, at some point down the line, if they want to put a bridge between the second floor of each building, they could, to connect the 2 conference centers. So we have that clear height. We wanted to, the program called for putting in a 250-person lecture hall with stadium seating in the building. So thought, okay, well, maybe there's an opportunity to carve this out of that volume. And we figured out a way to actually put a floor between the floors. So we're calling level 2 upper and level 2 lower. And we were able to get a lecture hall with stadium seating between those 2 floors, stepping down to sort of an overlook level. This is what it looks like in an axon. So we got sloped raker beams and just composite deck across the whole thing. And this lower level of the lecture hall is that level 2 lower between level 1 and level 2. This is what it looked like as of last week. I'll take a look at it today while I'm on site. But you can see what that lecture hall is. And yes, there is a column in the middle of it. That was sort of a compromise. And what ends up happening is we check the sight lines, made sure that nobody's going to sit directly behind it, but by having this sort of shallow curve, there's plenty of good sight lines on either side of it to a very long digital screen. So with today's methods of presenting and modern technology, we're able to make this really something that they don't really have enough of these on campus. They always book up. So I think this will be a sought after amenity when it's finished. And this is what it looks like in a rendered view. So there's that big digital screen that I was talking about, the column that isn't going to be a problem. People can admire it if they get bored during the lecture, I'm sure. And then for the rest of level 2 lower, outside the lecture hall is immediately to the left of the camera view. We create this sort of mezzanine level. You can walk through the lobby and look down on it, and some pre-function spaces and some seating. So it's just a great opportunity to create some flow through the building and create that connectivity that was, again, going back to one of the earlier slides, one of the main design objectives. And I think for my own benefit, we got this nice exposed brace frame with intumescent paint on it with some glass in front of it that it'll be like a sculpture, I'm sure. So I want to go back to the site overview to talk about some of the other odd things about the structure that we were working with. So level 1 is the current roof, future level 1. Same elevation as the plaza. You come off the doors into the lobby. Level B, come off doors into a lower lobby. Level A, there's a retail space with doors. But this parking garage here. So this is, I'm calling it level A plus 5 feet, because where the cars need to enter the building is wherever the bridge grade is. And that led to a need to pop up level 1 above that area to give adequate clearance, 8'2" for ADA wheelchair van. Right? So that's great, but this fan plenum that goes away. That's no big deal. That gets reducted. This is open to below for double high retail space, so that's fine. But this takes up the most valuable corner of the building, and it cuts off the lobby from everything else. So how do we deal with that and still get cars in there? So this wasn't designed as future floor structure. It's just metal roof deck, just 1.5 B deck with a PVC membrane. So, okay, well, we can take that off, but then what? This is the structure. Again, B deck on some metal roofing. See, this is the parapet wall that came down, was covered in EFIS, so that goes away. So we started, this is what it looked like in the field, but this was almost our theoretical starting point, right? We looked in the model and said, well, what if let's get rid of that, because we got to get rid of it anyway to do the structure. What does that leave us with? It leaves us with a giant hole. Okay, so now what do we need to get cars down there from that hole? Well, we started looking at things a little bit, and after some accommodation for MEP above here, roof drains and whatnot, but it's an awful lot of room for that ADA van that is maybe we don't need to have this whole thing bumped up. So maybe we can reframe this a little bit, hit our minimum clearance, and then go up, which is an improvement, right? It gives us back this lobby space, but we still have this thing here that's still 4.5 feet above the lobby floor. So what do we do with that? We got like a hill inside the lobby. We started brainstorming one day and thinking, like, well, what do you do with this? And thought, now you could put stairs up to it, and then what? So it took that next step further. Well, what if we continue the stairs and kept that going all the way up to level 2? And then what if we kept calling it the hill, right? So it's like, well, maybe we can make it a hill. Maybe we can do some kind of fake moss thing and make it a little green and add some benches. And so this is what we settled on, this atrium stair that comes up the hill, comes up, winds around, and then comes back up. So level 2 lower, level 2 upper, level 1, and the hill. And we turned it into, I think, what's really going to be the coolest feature of the building. This really sculptural stair that swoops around and curves and really it works with what's there. And something that left us scratching our heads for a long time in the design process, really, I think, this is the one thing that everybody keeps honing in on. And it was really just an accident of the constraints that we had to deal with. We got this nice little splayed column wrapped in stainless steel supporting it. So that'll be a nice little feature too. So I wanted to just to make some acknowledgments and some closing remarks on this. First and foremost, CHOP and the CM Gilbane Pride McKissick, a tri-venture. Owen Steel is our steel fabricator, ENR Erectors. I mentioned Elwood Specialty Steel and Elwood City Forge outside of Pittsburgh for those steel forgings that you can see in this image. And then RWDI did our wind tunnel studies. KPFF did a structural peer review for me. And Thornton Tomasetti, of course, was the original SEOR for Roberts Center and the Podium that we built off of. So, I wanted to make sure I left enough time for questions at the end here, because I'm sure there are probably some. And so I think we can open it to questions at this point.
Yeah, and everyone can feel free to either post a question in the chat and I can read it, or you can unmute yourself and just ask John directly. Well, John, I have a question.
Sure.
This was a really interesting project, a lot of challenges that you've presented, and that there's been some unique solutions to those challenges. I guess the design started in 2021. When did construction start, and when is it anticipated to be complete? I guess substantial completion.
Right. So design started in January 2021. We did some early site packages for demolition and procurement of long lead time items, particularly electrical these days. If you've been involved in that market, lasts more than a year. So that happened in October, actually almost exactly a year ago today. So it was right at the end of October when we issued for that first part of construction. And in November, almost I think the week after, they started mobilizing on site. The Podium helped us a little bit in that regard, because construction and demolition really started getting going at the end of January, but they were able to do a lot of those foundation retrofits and really right up to the micropiles while the building was still enclosed. So they had a climate controlled, weather controlled area to work in over the winter time. And then when spring rolled around, they stripped off the EFIS and started getting the steel in.
Great. So when is the anticipated substantial completion?
So August of 2025 is intended to be day one completion, substantial completion for day one occupancy. And what that basically means is first research group moving in, the podium of the building turned over for the lobby, but level 2 fit out continuing. And then most of that day 2 type work completing in January 2026. And then over the course of that year, additional lab groups will move into the building, either from outside institutions or from across the river in outmoded lab space.
Great. We have some questions in the chat. So the first one is, what material were the cast connections made from?
Yeah, so the steel castings, I'm going to go right back to that image. Back here. Okay, so these castings were made from, I don't remember the exact grade of steel, because the steel forgings it's a different thing than you'd see in your steel construction manual. But it's essentially the steel forging equivalent of ASTM A572 grade 50. There's different toughness tests, but it's the functional equivalent. And material yield stress wasn't really a governing design of the block itself, because it was it's a big block of steel, so there's more area than you would actually, you're not using that full grade 50 like you are for the column. But just a side note on this, Elwood Specialty Steels they make these blocks for a lot of other forgers around the country, or other fabricators around the country, rather. And they actually do. I'd love to show you photos from that process. I got to tour the plant where they go right from electric arc furnace into the forging and then into fabrication. It's fully integrated. But they don't let you take pictures because they're the same material as what they use to make the crankshafts for nuclear submarines. So there's a national security issue there. But it's the amount of quality control on these, because they're so used to that high precision, is just it's impressive how the precision to that these blocks are milled to, far beyond anything you're used to seeing in a building.
Yeah, that's interesting. So we have some additional questions. The next one is, could you speak to some of the analysis software you used overall and for connections specifically?
Sure.
Pros and limitations you faced with them.
Yeah. So I'll say first that there are lots of different kinds of software out there. I'm always hesitant to speak about specific ones. I don't want to endorse or anything. But with that caveat, for global structural analysis, we use a little bit of everything because there are so many unique conditions. That includes RAM, RISA, ETABS, the usual suspects. For connection design, of course, spreadsheets are always a great starting point because it gives you a nice gut check. For finite element analysis, a little bit of RISA, but mostly Idea Statica, which seems like they're buying a lot of advertisements these days. I had worked with, I don't know if anybody here has worked with Dave Eckrow before. He was with SidePlate for a number of years. He's their product rep. And I had done SidePlate buildings before. And when he moved over to Idea Statica, we kept in touch. And we got a chance to try the software, take it for a test run. And it seemed like it fit this project pretty well because we have so many. This isn't uniform force method, right? This is some different condition variation of uniform force method, but uniform force is really just an idealization of force flows anyway. So it tends to lead, especially the further you deviate from it, the more restrictive it becomes, and a lot of members start quote unquote failing just based on what's assumed for force transfer. So Idea Statica or similar programs for finite element will actually look at the way the force flows based on the way materials deform. So pros and cons. I think pros are, like any software, there's a learning curve, but once you learn it, it's all very much repeating the same processes and it becomes very fast. It's a good, fast program. Cons, I think, are, another pro is that it directly checks the AASC limit states for welds and bolts, which is great because that tends to be what matters the most. Cons, I think there's some restrictions a little bit on how members are supported. It'll assume that if you have members in bearing, that all the force transfer is through weld, which it isn't, it's through bearing. So you might get welds failing when members are in contact, but the weld isn't actually transferring any force. Another one is that for the limit states of the members themselves, you have to really understand how a buckling analysis is conducted and what that means based on material yield and understand what that is, because it won't directly check like chapter E or chapter F for flexural or compression provisions because it doesn't really apply in a plastic analysis. But I guess that's probably true with a lot of finite element software. And again, there are others. But I think with any of the software I just mentioned, if you're not familiar with it and you are interested in it, most companies are very willing to offer free trials. And whether, this project or others, that's usually how we decide in our firm to try a new software. We take it for a test run on a project. If we like it, we'll get a license for it. If not, we'll try something else.
That's great. So yeah, I worked a little bit with connection design and am familiar with SDS, but I hadn't heard of this Idea Statica. So it's IDEA.
Yep.
Like idea.
Yep.
And Statica. Okay.
Yep.
Good to know.
Exactly. Yeah.
Okay, next question. As you took on the project, how did you approach your structural fee, design, bid, construction for such a unique design and hands-on construction support?
Yeah, that's a great question. If anybody has the magic bullet for this one, let me know because I think I don't know if anybody does. So, in an integrated design firm, it's one benefit. It's actually a big benefit of an integrated design firm is we can go in with an overall fee to the project that we can be confident at a high level that it'll work for architecture, MEP, structural. I mean, we're doing this soup to nuts, all those services plus graphics and lighting. And we can be confident on an overall fee with a clearly defined scope of work and clear exclusions. And any good fee proposal will have that. But if we find that, mechanical goes a little bit over their fee in the grand scheme of things, it's balanced out, right? So if I'm a little under, mechanical is a little over, I don't have to sweat it too much at the end of the day. There'll be not necessarily everybody who leads that discipline will see it that way, but in the grand scheme of things, that helps. So I want to get that out of the way, that makes for those of us that are at, my firm or something like Ballinger or another integrated firm, that's often something that can be relied on. But for the structural fee specifically, it was about looking at past project performance. We've got a decades long experience doing all kinds of different projects. And I can pull from a spreadsheet that we have that looks at the construction value of a project, where it was located, when it was done, and what the scope of work was, what the fee was, and how we performed on it. And the first step I usually take is a top-down fee, especially when it's a complex scope like this, percentage of construction value. And then I look at that against what that track record is and see, okay, I'm in the ballpark. You have to adjust for inflation and things like that, but it's all in there. And make sure I'm still within that range. If I'm way high or way low, that's the first red flag that something's wrong. Once I get to a comfort level with that, it's about thinking about those past projects and maybe even talking to people who worked on them if it wasn't me and seeing, is there anything different you would have done? Any exclusion, something that came up later on that you were kind of kicking yourself for because it wasn't an exclusion, you got stuck with it, it was added scope. So that gets you to your day one fee. And then if you have that design scope clearly established, then you could talk with the client too, make sure they understand what that scope is. Because if everybody's on the same page day one, you have a good client, CHOP is, if and when there's an ad service down the line for a field condition that came up, like the duct bank below the caissons that, wasn't really, survey showed it over here, it turns out it's over there. Everybody's on the same page. They understand that, that's extra work for everybody and that needs to be negotiated. So it's not a clean answer to your question, but like I said, if anybody has a clean answer, I'd love to hear it because it's a lot of work. I know I'm sure a lot of people on this call are responsible for developing fees and then held accountable if it goes sideways. So, yeah.
Yeah, I think that's a great answer. And like you said, it's a hard, clear-cut answer to provide. We have another question regarding the castings again.
Mm-hmm.
How much design did you do versus what was designed by the fabricator or delegated?
Yeah, so this is what I designed essentially. Note 2 basically says that here's all the forces, right? Here's all my brace frame forces. Note 2 just says you can design this with a solid steel node casting here if you want to. And it provides basis of design criteria. I wanted to leave it up to the fabricator because I mean, I had Owen Steele who's actually done something like this before. But if I didn't, and it was a fabricator unfamiliar with it, they might have said, we've done these complicated connections, we're set up to do it. So I'm glad that they did what they did. I think in the end, it was, I want to say, my numbers could be wrong here, but I want to say it saved like $30,000 in shop labor at a $7,000 material premium or something like that. It was more than a 2-to-1 savings by doing this versus standard fabrication. And you know, they took that information in their bid, right? They said, we can do this with that, and therefore our fabrication cost is going to go down, and that'll make our bid more competitive.
Wow, interesting. Yeah, I guess with adding all those stiffeners in, if they did it the other way, that could be a lot of fabrication time. So
Especially on heavy members like this, where you have to do all the preheat. So
yeah,
it's a lot.
wow, interesting. Well, that's all the questions that we have in the chat. I guess I'm going to send the link in the chat for the PDH.
Perfect. We ended at exactly one. So that's those.
Yeah, and I just want to, so first, I guess if there's no other questions, I want to take over and just do a quick SEI outro plug. I guess first, we want to thank you, John, for your time. This was a great presentation. And I just want to make a note of SEI's upcoming events. So next month, we're planning on doing a student event at Temple, which will consist of a panel discussion, typically more heavily attended by engineering students, but we open it up to professionals as well. Our December meeting is planned for December 7th. A representative from BDI will be presenting on a bridge diagnostics topic, and that's planned to be an in-person meeting. So hopefully everyone can attend. And just another note on our planned golf outing for May 10th. So mark that in your calendars for 2024. All right. Well, thanks again for joining us. And thank you again, John.
Thank you. And again, if anybody has any other questions, feel free to email me, and I'll try and get back to you as soon as I can.
All right. See everyone later.